David Lynham. I'm a global project engineer and lead Moldflow analyst for Trend Technologies. Today I'll be talking about in my presentation reverse warp workflows, theory versus reality, and I'll be looking at an amorphous polymer case study and also a glass-filled semi-crystalline polymer case study. The contents will be a quick bio on myself, an introduction to our company Trend Technologies, case study 1, which covers amorphous polymer, a reverse warp workflow. Case study 2 is glass-filled semi-crystalline polymer reverse warp workflow. Conclusions on the 2 case studies and some take-home notes on reverse warp in general. So a little bit on myself. I'm the lead Moldflow analyst and trainer for Trend Technologies and Moldflow. I'm professionally certified by Autodesk. I'm hoping to go for expert certification in the near future. I've been working as a global project engineer for Trend for around 5 years, delivering technical injection mold tools into multiple production facilities across the globe. Here in Trend, we see Moldflow as being like an integral part of our successful on-time delivery of injection mold tooling projects to all of our customers. So introduction to Trend Technologies. We're a global contract manufacturer in the plastic injection molding, metal stamping and metal fabrication industries. We've decades experience delivering injection molding projects in the automotive, healthcare and life science, industrial, enterprise, digital home and office sectors. Ideally, we have a global footprint with 5 major injection molding production facilities, one in the US, in Chicago, one in Guadalajara, Mexico. I'm based in Trend, Ireland here. We have one in Martin in Slovakia and one in Johor, Malaysia. So here in Trend, Ireland, we actually manage all the plastic injection mold tools globally for Trend. So we deliver projects into all the other sites. We've been utilizing Moldflow Advisor and Insight products for about 10 years now. We started out with an Advisor Ultimate license around 10 or 11 years ago. And about 4 years ago, we purchased an Insight professional license. And it's really grown from there and taken hold, and it's become a pivotal part of our whole process now. So we see Moldflow extensively as like a risk mitigation tool, and we'd use it from as early as a new quotation comes in. We'll use Moldflow Advisor on it right through to maybe solving problems in production. Ideally, we don't want to be bringing problems into production. We like to solve the problems using Moldflow before it actually gets to production environment. And it definitely in Trend we see Moldflow as being one of our cornerstones to our tool development process. So just an overview of our footprint here again. So quite ideally, I think here in Trend, Ireland, we're quite well based in terms of a time zone, so we can work with the West, with Mexico and the US in the evenings, and then early morning we can work with Southeast Asia in Malaysia. So it works quite well, and that's how we manage the tool builds, I think, from Ireland for all the other sites. So I suppose the importance of Moldflow in our whole tool development process and where we use it, I suppose. So as early as RFQ, when we're trying to validate our quotation, we want to make sure we've got the correct cycle times, clamp tonnage, highlight any tick sections to the customer, and really kind of a backup for our RFQ and make sure we're accurate and competitive to try win the business. And if it gets to the next stage and we get to our technical review with the customer, we can use Moldflow, present it, show them some potential problems with warpage, filling, anything like this. We can show them. They always like to see that. If we're awarded a project and we get to the tool GA, we want to optimize our gate locations. Where are we placing the hot runner? Does it work in our tool design? Have they optimized the cooling channels? This will all be analyzed and verified through Moldflow and fed back kind of with our tool makers in mind. Then when it gets to the next portion of developing our process, our injection molding process and maybe measurement method, we tie in Moldflow here. So we use we'll export warp files, have a check of what the warpage is like, what's predicted compared with the drawing, develop our molding process within the software and use this process as a starting point at our first trial. Because it gives a good, rather than a process engineer having to go and develop process from the beginning, Moldflow gives them a good starting point to go from, and it shouldn't vary too far from what Moldflow is predicting. And when it gets to the later portion of this, like the FAT and PPAP stage, we'd ideally not be wanting to pull back and use Moldflow here, because if everything else has gone right from what we've done, hopefully there'll be no problems at the FAT or the PPAP stage. But it's really how Moldflow can be used throughout our whole tool development process. So the first case study then is an amorphous polymer reverse warp workflow. So the component was this top housing you can see here. The material is PCABS, Covestro Bay Blend T65 XF. So the material was really well characterized within the Moldflow database, gold standard, and it had CRIMS testing. So we could rely on potentially good, accurate warpage results for this material. So the meshing and modeling for this component, a dual domain mesh was modeled. This was based on, I think, what was recommended by Moldflow, but also that the match percentage was above 90%. So it was going to be good at a high enough standard to give us really accurate warpage prediction. It's a 4-cavity tool in reality. I modeled 1 cavity and accounted for the other 3 with occurrence numbers. And due to the box shaped nature of the component, I used corner effects. I simulated the corner effects as well. And just to show that the full tool detail from the nozzle down was modeled into the simulation as well. So workflow and optimization from a warpage standpoint, typically with any injection mold tooling project, I'll always follow the standard procedure of optimize your gate location, optimize the filling and the part, balance your runners, size your runners, optimize cooling, optimize your packing profile, review your warpage. Is it okay? Is it not okay? And this is the standard approach. I think what differs this time around is due to the boxy nature of the component, the open end of the box will always have a tendency to bow in due to a lack of structural strength. So it became a bit of a challenge in this case, and I'm going to go through in the upcoming slides of kind of challenges we faced and how we overcame them. So just to go through, it's all well and good. I say I optimized all of these steps, the gating, the cooling, and the filling, the packing of the part, but I actually want to show that I did go through all these steps and really got to a point where I exhausted the optimization process by standard workflow. So 2 allowable gate locations were investigated here. On the left, we had on the longer side of the component a central subgate. This led to about, let's say 1.3 mil warpage in that x-axis, so the box was closing in. Then with a gate on the side of the part, we reduced this slightly, about 0.12 mil less warpage. So this was the decision around why we decided to use this gate. And going into optimizing the fill. So again, the original components, some short shots were predicted on pin sections around the clip here. It becomes a bit of a catch-22 because the clips have to be flexible enough to go over the mate and cover component. But I suggested adding about 0.2 mil thickness here, which still worked for our customer, and it relieved the short shots and made a much stronger weld line there with more homogeneous melt flow front temperature at the weld line formation. Optimizing the cooling then. So the goal for this part was to achieve a 25-second injection pack cool time, and obviously for differential cooling to have minimal impact on part warpage. So we didn't want cooling to be one of the driving factors in our warpage result. So originally with our cooling here, we had 2 baffles on the core and we used a single cooling temperature of 65 degrees. This led to some hot spots in the tool up in the top corners and quite a wide range in terms of mold temperature there as well, about 35 degrees. This then had a knock-on effect into our part warpage caused by differential cooling. You can see it's about 0.35 warpage was being caused by differential cooling, which is probably unacceptable, and we want to improve this. So to go with this, I suggest using 15 degrees lower in the core. I evaluated this. We tightened that gap much more. We had about maybe between 60 and 85 degrees between minimum and maximum mold temperature. And this led to part warpage, which was much better. There was almost no impact from differential cooling, especially on the opening of the box, which was the kind of critical area for us. So optimizing packing then. So again, trying to just get this warpage really down to the minimum amount. The original gate proposed by the toolmaker was 1.2 mil subgate. I suggested open this to 1.4, and this gave us around 1 second extra on our packing time at 65 MPa. This improved our warpage by a further 0.1 of a mil, and now our X, Y, and Z shrinkages were matching more closely to the 0.6 nominal shrinkage for Bayblend T65XF. So then after going through this kind of optimization process, we got to these parameters, which was an injection time of 1.6 seconds, VP switchover at 98%, packing pressure 65 MPa, for 7 seconds, cooling time 16 seconds, melt temperature was 270 degrees. And as you've seen from the previous slides, the core temperature was set to 50 and the cavity set to 65. That was the optimized process parameters, and we'd really, at this point, I felt like I'd exhausted through standard procedure, the process and the optimization of this part in terms of warpage. So then reviewing this file now, basically within Moldflow, you can actually export a warp file after you run analysis. And what I typically do is I would compare this warp file to Nominal CAD or to the tolerances on the drawing. So for lengths and widths on a clip feature and the length of from the top surface to the clip, there was specifications we needed to meet on the drawing there. And after the predicted warp file after process optimization was very nominal, really good results here, and there was no issues. The problem arose when we looked at a critical dimension on the drawing, which was this 21.39 plus or minus 0.25 millimeters, the opening of the box, which we needed to measure at three locations on the component A, B, and C. So even after our process optimization, we were getting good nominal lengths and widths. The part file was still warped by respectively 0.4, 0.6, and 0.3 at A, B, and C. So this became a problem, and it kind of led to, okay, well, what's causing our warpage? Is there anything we can improve? So the real cause of warpage was corner effects here. It was just due to the actual design of the component, the boxy shape. You could see our differential shrinkage and differential cooling were quite minimal. Below 0.1 of a millimeter was actually caused by those effects. It was really corner effects solely causing this warpage. And this brought about, right, well, if we keep moving forward with this, we have what's an optimized process, and if we use it, we know we're going to have problems with this tool when we trial it in reality. So going through this, we knew when we analyzed the file, we ended up with this resulting warp file with the shrinkage rate included, and we were still too small on that dimension, that 21.39 dimension. So at this stage of the project, I really started to look at, right, well, what options do we have? And I knew Moldflow has a reverse warp file output within it. I investigated this. Obviously, when you export a reverse warp file from Moldflow, it actually exports the file, but it includes the shrinkage rate as well. So you don't actually need to add a shrinkage rate or do anything. You just export the file without affecting shrinkage on the warpage result itself. This will give you a file you can see here on the bottom left, where our sizes are bigger. It's 21.96, 22.1, 21.83. So it's actually given compensating shrinkage and that warpage, that bowing effect that we have. So I reanalyzed this file within Moldflow with the same process, optimized process parameters I had, and the resulting warp file led to really promising results. So we were within nominal to 0.03 of a millimeter. So in theory, excellent result, kind of theoretically within Moldflow, brilliant. So again, looking at this is a GOM Colour map of where we would have been if we kind of used the Nominal CAD file. You can see really bad bowing in of our opening there. And then when we reanalyze the reverse warp file and overlaid this on Nominal CAD, the opening was within plus or minus 0.05 of a nominal. So really, really close to nominal. So this brought about, right, what do we do? I think based on the material characterization, it's gold standard, it's CRIMS tested, and the results were really positive when I reran the analysis. I thought, like, it's risk adverse. I'm going to actually implement this reverse warp on our tool. So luckily in this scenario, the warpage was actually localized to the open end of the component, and it didn't cause any undercuts when the toolmaker looked at the reverse warp file and used it. So it was quite clean. They could basically use the file directly in the steel, and it was an agreement between Trend and our toolmaker that they would use this file to overcome this problem. So when it came to trial time on the 4 cavities, here's just a result. So basically all cavities well within specification. The max percentage of our tolerance used was 22% on one of the cavities, but very, very nominal result and really good on our first off samples. So really positive. And then comparing now, I think an important slide is looking at our tolerance band. We had what Moldflow actually predicted, which is in blue here, and the 4 cavity results on the actual part, and what would have happened had we not used reverse warp at all is in red down the bottom. They've been well outside our tolerance and had a really difficult challenge in terms of like correcting steel and how do we compensate this warp now when it's set in the component. So really, really successful kind of use of reverse warp for us here. It came in really, really well. So looking at our case study 2, which is going to be a glass fill semi-crystalline polymer reverse warp workflow. So this was a shielding cover component. Our material was PBT glass fill 30, Ultradur B4300 G6. Again, the material was well characterized in Moldflow, and again was CRIMS tested. So I suppose we could take high confidence in the reliability of the warpage results. Meshing and modeling. Again, dual domain mesh was modeled. Our match percentage wasn't completely at 90%, but it was very close, probably good enough to rely on the results. Again, it was a 4-cavity mold. What's interesting in this one, basically, due to kind of the difficulty around glass filled semi-crystalline polymers, we used actually a development cavity here rather than using it straight into our production cavities like we did with the Amorphous one. We have a development P20 cavity that we're going to trial on its own and develop our sizes, test the results, and then based on confidence there or how successful it is, we use these sizes on our production cavities if it works well. So again, it's a boxy kind of component, so corner effects were simulated. So I'm not going to go through again, but I went through the loops of optimizing the workflow here, part filling, cooling, packing, and got to a point again where I felt I couldn't do much more through standard optimization. I'm really started to think about, right, I'm going to have to look at reverse warp here and test out whether it's going to be successful or not. Difficulty again with this material is you're not usually just going to have one impact causing warpage for you. So in this case, it was the shape of the component, it was the differential shrinkage, and the glass fiber orientation dictating how our part warped. So again, here was the optimized process parameters I came to. It was a 1.5 second injection time, packing pressure of 100 MPa for 5 seconds. So with these materials, they tend to freeze off very quickly because they have a high transition temperature. And a 9.5 second cooling time, melt temperature at 265, and cavity and core water temperatures were 75. So there was no differential temperature used from cavity to core. So some of the challenges we faced with this component were we had some tight geometric tolerances, and it was quite a large component. It's 100 by 120 mil, so it wasn't that small. We needed to meet flatnesses of 0.3, positional tolerances to 2 datums of 0.2, symmetry of 0.2, parallelism of 0.2 as well. So some really challenging tolerances on a part this size using this material. So again, reviewing the cause of warpage, our dictating factor here was actually orientation effects, but coupled with differential shrinkage and corner effects, which cannot be ignored as well. They both had quite like 0.75 from differential shrinkage on our warpage and 0.35 from corner effects. So we had really 3 main areas affecting our warpage, but fibre orientation was definitely the dictating factor. Looking at cooling then, it really had minimal impact, so less than 0.05 of a mil from differential cooling. So we could just kind of ignore that as a problem area. So again, the decision here was made, right, we'll look at using this reverse warp model in the software, and I had to go analyze this again. So here we're looking at what another GOM 3D scan output of the Moldflow Warp file versus Nominal CAD. So we had some really high warpage, especially on the back wall, up to nearly 1 millimeter, about 0.9 of a mil, and some warpage on our bosses there, which have a critical flatness to them as well. Then when we looked at reverse warp and reanalyzed it, look, we didn't get to a perfect scenario, but it was definitely a lot closer to nominal. So the scale on the previous slide was plus or minus 1 millimeter. The scale on this slide is plus or minus 0.25. So it shows how much better we were closer to nominal using the reverse warp in theory in the software. So the decision was made now, right, we're going to go with a reverse warp file because it will get us to a better place at our first off tool trial, closer to meeting drawn specification. Some of the challenges now with this component, we had some deep ribs on the component. We had long bosses on the component. When we actually use a reverse warp model on this, what happens is it creates undercuts in the tool, which aren't going to be in line of draw. So this becomes a bit of a head scratcher, and you're like, right, well, obviously this isn't going to work as it is. So what happens is our tool designer will actually take the model, have a look at some of these undercut areas, change the draft angles, wall section in some areas, and he'll actually make a hybrid, what I call a hybrid reverse warp model that is in line of draw, but is trying to compensate a lot of that like unwanted warpage effects as well. But the key here is it's not identical to the reverse warp model from Moldflow. So you can see here on this back wall, I've highlighted that we're about 0.1 of a mil less thick on the back wall due to this undercut that was there. So this obviously brings about its own challenges. So just highlighting some, I suppose, key results that would be affected by the changes in this hybrid model. So our fibre orientation is not the same as it was now. You can see here highlighted in this circle where our fibre orientation has now changed, and this is our dictating factor in warpage. So any change in fibre orientation is going to have an impact on our warpage and change the magnitude and direction in some way. That's a challenge there as well, and some change in our frozen layer fraction. So basically, we have to thin out certain areas because of these undercuts and get the wall section in line of draw, but it caused the part to freeze off slightly earlier on our hybrid model. So due to this, we basically, if we look at what would have happened if we could have used the reverse warp file directly from the software and reanalyze it, we'd have been very good. You're talking maybe plus or minus 2.2 of a mil off nominal was predicted. But then when we used this hybrid model and reanalyzed it, we got some anomalies where obviously we had changed things in the file. We're going to get a different warpage result. Again, definitely more positive than was predicted when we used a nominal CAD file, but we did have some bulging here on the back wall. You can see 0.4 of a mil bulge there. And one of the bosses was predicted to warp as well. So not perfect, but again, looked better than we were beforehand. So this slide is comparing if we use no warpage compensation and the actual first off tool part from our development cavity that we had. So you can see here we're up at 0.9, over 0.9 mil warpage on the back wall, 0.85 here in the top corner of the part. We had some really heavy warpage predicted if we had no compensation. And with our hybrid model that we used on this development cavity, this was the actual first off tool result. You can see the bulge on the back wall was actually quite well predicted and similar magnitude as well. And the bosses were quite flat in reality, where I think Moldflow predicted maybe they wouldn't be on one of them, but all in all, quite a positive result. So then theory versus reality here will be comparing what did Moldflow's hybrid reverse warp model reanalyze predict versus what we actually got. So again, the boss was predicted to warp in Moldflow. We didn't actually see this in reality. It was quite flat, a little bit the other way actually. But these two, we did have two anomalies that jumped out where the part tended to bulge in reality on the top surface and on the back wall that just wasn't predicted in Moldflow. But all in all, some good correlation, and it definitely got us to a point better than if we had just used a nominal CAD file and a single shrinkage rate. So looking at a measurement report comparison. So the first one is the top result is really looking at what that warp file from Moldflow would have been, and we predicted we would be about 30% out on dimensions on the drawing had we just used a nominal CAD file. And what we got on our actual FOT measurement result on the part was 14.3% out of spec. So almost 50% improvement there. So successful, by no means perfect. It wasn't a success story from case study 1 where we literally solved the problem in first hit. Obviously, we still have nearly 15% of dimensions I expect that we need to address now, but quite a positive result. So the conclusion then on case study 1, luckily the reverse warp file could be used directly to machine steel to, as it did not contain any undercuts. The implementation of the reverse warp file was very effective, and it helped us meet our customer specifications first time. The simulation versus real life results were really, really similar. The use of the reverse warp file saves us time and the costs associated with additional recuts that would be necessary to address this level of warpage. So all in all, I think for the amorphous polymer, it worked really successfully and really helped us out. The second case study for the semi-crystalline glass fill polymer. So due to the magnitude and direction of warpage, the reverse file led to undercuts which needed modification to be manufacturable. Because we had to use this hybrid file, the actual reverse warp file differed from the hybrid warp file warpage. And this was caused kind of by changes in the fibre orientation and part thicknesses, which I covered on the slides previous. But again, it led to a slight change in our warpage. So the reverse warp implementation improved our predicted versus actual out of tolerance dimensions by still around 50%. So quite a successful result. But again, you can see there's a lot more challenges when you use a semi-crystalline glass fill polymer versus maybe a standard PCABS amorphous polymer. So just some take-home notes from the presentation then today will be, I'd say before attempting reverse warp, the injection molding process parameters must be optimized using the standard Moldflow optimization workflow. So I would say reverse warp should be implemented as a last resort to address warpage problems, not the go-to solution. There's no point in using reverse warp if you have not optimized process parameters within the software. Otherwise, you're going to have a lot of problems. Like if your part hasn't froze, your gates haven't frozen, you should not be using reverse warp flow. You need to go through the standard workflow optimization first. Reverse warp should only be used if the material is very well characterized for filling, packing, and warpage in the Moldflow material database. You could see I highlighted it in it how important it is, the characterization of material, and especially for warpage results. If you're using a dual domain or mid plane mesh, you should make sure it has CRIMS data as well. Look, if you use your own material and you've got really good testing done already between a material maybe that isn't that well characterized in Moldflow, but you've proven that the results are accurate in reality, then maybe you can use a material like this as well. So depending on the part geometry and direction of warpage, reverse warp models may have undercuts. In this case, a manufacturer hybrid model must then be reanalyzed and verified against the drawn tolerance requirements. So I think when used properly, reverse warp files can be a great output from Moldflow to help combat unwanted component warpage. Utilization of reverse warp techniques inherently becomes more complex and tricky when using glass filled semi-crystalline polymers. So I think the case study 2 really shown that you have a lot more challenges when you're using semi-crystalline glass filled materials. Okay, so that concludes my presentation on reverse warp workflows. Thanks a lot for your time and listening today, and hopefully you can take something from the presentation.